Today, Fourier Series, made easy. Here's a typical exam question. A Fourier series for a function f with period 2l, and that just means that the function repeats every 2l, has this form. That's the Fourier series. Or if you don't like the summation notation, you can see here it's an infinite series of sine and cos functions. So in some ways the task is very simple. If you want to answer the exam question, you just need to work out L and all the A terms and all the B terms. The real problem is, but there's a lot to remember. You have to remember the Fourier series formula and then the formulas for the A's and the B's. Amazingly, in less than 10 minutes, I can show you how to work out these A's and B's from first principles, and then you won't forget them in an exam, and it'll make it very easy to remember the Fourier series formula. And if we work out these A's and B's correctly, then Fourier series is a very good way to describe a function. Here's the function that we're given in the exam, and as we start to add more terms from the Fourier series, you can see that very quickly we start to get a good approximation to the function. Okay, here's the exam question, and the first thing that we need to do is work out L. And if we look down the bottom, we can see that fx plus 2 pi equals fx, and that tells us that the function repeats every 2 pi, and so L equals pi. And often actually examiners will give you a period of 2 pi because it makes the calculations easier. So here's the generalized Fourier series formula that we had up before, but we now know that L equals pi. So let's go ahead and put L equals pi into that. And so now we have a Fourier series for the specific situation where the function has a period of 2 pi. Now we have to work out the A's and the B's. I'm going to work out one of them, and it'll be pretty obvious how to do the rest from that. So if we look here, we can see there's a B3 sine 3x. So I'm going to work out the B3. So to do that, I notice that after the B3 we've got sine 3x, so I'm going to multiply both sides of this equation by sine 3x, and I get this. Now I'm going to integrate both sides with respect to x between negative pi, and I get this. Now to proceed further, we need to realize that most of what's on the right hand side equals 0, and this is a very beautiful and useful property of sine and cos, and it really tells us why the Fourier series uses the sine and the cos functions. If we look at all these integrals on the right hand side, they're all a sine of a counting number times x, and or the cos of a counting number times x, and almost all of these integrals are 0. So wherever we have the cos of an integer, a counting number times x, 0. Wherever we have sine of a counting number times x, 0. Wherever we have cos times sine, 0. Wherever we have cos times cos or sine times sine, we'll get 0. With the single exception that when the two terms are identical, as you can see on the right hand side here, then we get pi. What this means when we go back to trying to work out the value of B3 is that all the terms on the right hand side are equal to 0, with the single exception of the expression with B3 sine 3x sine 3x. And that right hand side equals B3 times pi, as we've just seen, and so that enables us to work out B3. And we can use the same method to work out all the A's and all the B's. The only one that might be a little bit different is the A0, which we have here. This is the original Fourier series. To work out A0, we just take the integral with respect to x between negative pi and pi of both sides, and all those terms with sine and cos we've seen will just drop out to nothing, and we're left just with a term for A0, which we can solve for. And so that means that we've now worked out all the A's and the B's, and here are the three sorts of formulas. There's one for the A0, one for the other A's, and one for the B's. So we've made considerable progress. We've discussed and worked out the L, and we now have expressions for all of the other terms that we need, the A's and the B's. So if you now want to go and apply that to an exam question that you have or a homework question, well, now's the time to stop the video and you can go off and do that. Otherwise, I'm actually going to go through and work out these integrals and in the process give you a few tips. So the first tip is this. The examiner is not really testing you on your ability to do integrations. So generally they will pick a function so that some or most of these A's and B's will equal 0. And that is in fact the case here. So the first thing is, what's A0? A0 is really the average value of fx between negative pi and pi. Or alternatively, it's the area under the graph between negative pi and pi, taking into account sine. So if we go and have a look at the graph again, we can see that the average value of the function is 0. So we'd expect A0 to equal 0. The next thing is the function f is an odd function. That is, f of negative x equals negative f of x. And where you have an odd function, you expect that all the expressions with cos will also equal 0. In other words, all the a terms will equal 0. So we're going to expect all the a terms to equal 0. If by chance you have an even function, that is f negative x equals f of x, well then you expect all the sine functions to be 0. So now let's have a look at the integrations. So here's the one for a0. We expected it to be 0, and in fact the integral tells us that a0 does in fact equal 0. Next, we expected all the other a terms to equal 0, and here's a calculation. Now I've just put here n can be any integer, 1, 2, 3, 4, 5, whatever you want. And you can see that irrespective of what n is, we always get 0. So that's also good, and so that now just leaves us to discuss the b constants. So you can see my calculations, and we've got an answer in the middle there for the value of bn, where n is a positive integer. If I now feed in an even n, I get 0, so that means that b2 equals 0, b4 equals 0, b6 equals 0, etc. For the odd n's, I get b1 equals 4 on pi, b3 equals 4 on 3 pi, b5 equals 4 on 5 pi, and now you can see the pattern. So for example, b7 would equal 4 on 7 pi. If we now return to the Fourier series formula that we had for fx, we can now feed in all the values of a and b that we've worked out, and we end up with this expression here, which is the Fourier series for fx. And if you like, you could just take out the common factor to make it look a little bit neater, and that'll give you the final answer for the Fourier series for fx. And that should get you pretty much full marks. That's it for Fourier series made easy. I hope you found it useful.